Okay, we're going to be talking about how to compare distributions. So, first thing I will say is, first thing I'll say is I will be using the slides in this mode, as annoying as it is. That's deliberate because I have notes and I can't see the notes otherwise. So, this set of slides is not so much for evolutionary computation specifically. This is going to be useful for like anything, especially if you do anything more like data science, machine learning. I will also say that I'm not a statistician and I'm probably going to use the wrong words all the time. The point about what I'm showing you is to give you the intuition as to what you're actually looking for when you are comparing things. We're interested in comparing distributions. And the king way to do that is a permutation test. And there's going to be a lot of things. Like raise your hand if you've taken Stats 101. Okay, so is that really it? Isn't it like a required course for... Oh, it was for me.
The stats for students in science.
Oh, well that's... Okay, when I said Stats 101, really what I meant was like stats, right? Okay.
There is a stats report.
All right, so raise your hand if you've taken a stats course where you've ever learned about a t-test or something. Okay, great, perfect, great. So there's a lot of things you've heard of. Like, oh, the Null Hypothesis, and that means we assume there's no difference and all. All of these things that you're like, okay, there's these arbitrary rules, like we assume this and then we go. These are all going to hopefully fall into place today. Because this right here, this idea of a permutation test is going to be, or a randomization test if your data's too big, same idea. This is the king of how to compare distributions. This is the way you do it. All the other things you're doing are tricks to do it quickly and easily. So if we have something we're observing, I don't care what it is. The arrows, I guess, don't transfer well on Google Slides. I've got this object. It's this gray cube sitting there. It's something I can observe. And we might use a fancy word like, oh, a random variable that keeps spitting out values over time. Maybe the thing I'm observing is how many eggs that fish lays. Maybe it's how many people on campus how many people in this room today have blue eyes, whatever it is. It's something we're observing where information comes out. And every time I get a piece of information out, I'm going to record it, right? I'm really interested in it. How many eggs is that those fish lay? And I want to come up with a hypothesis of like, well, the fish in the Atlantic coast lay that many, but the fish in the Pacific coast lay that many, and that's different. Wow, that's interesting. But the question is, are they different? So whatever, I've got this one random variable, I've got this dark gray box spitting out numbers. And I'm going to observe it for a while, for as long as, I can in a reasonable time frame. And I'm going to record all the data I see. If this is the fish example, each one of these will represent each fish laying eggs. If this is the students with blue eyes, that might be on like a given day or maybe a different course or something, whatever. I'm making some observations. And I'm recording it. Maybe it's the temperature outside on a given day. Whatever, it doesn't matter. I've just got something I'm observing, and I'm recording it. And if I record it, I can generate a histogram. We all love our histograms. The histogram is showing us the distribution of those values. So if I keep observing this over and over and over and over again, and I keep track of how many times I see each value, I can plot this chart. The key critical question you have to ask yourself right now is, do you understand what a histogram is? This is important before we go. If there's any questions about it, ask now. Okay, so it's just this nice, it's a count of how many times I observed a given thing. This is obviously assuming we have a discrete thing where we have nice separate values. We could generalize this to continuous values, but then we would, kind of give it in a range. If the value falls between 1 and 2 and 2 and 3, that way you kind of deal with the fact that there's an infinite number of values between 1 and 2. So there, great. This dark gray box gives me that distribution. This light gray box, the numbers it's spitting out, look, the numbers that we're seeing are clearly rather similar, right? But when I plot the distribution, it looks a little different. Do you see that? Now the funny thing is, when do I stop observing values coming out of those random variables? When do I stop? Do I record it for a day? Do I observe 100 fish or 1,000 fish, right? Because the thing is, if I observe 100 fish, I get that distribution. But if I observed 1,000 fish, the distribution might really change, right? Maybe it just fills in more. Maybe I just got really unlucky and the fish I started observing were all sick that day. I don't know. But, we've kind of got this question of like, well, how many observations where do we cut it off? But okay. So if I go here, I've got these two different random variables. Maybe the dark is like the fish in the Pacific Ocean and the light is the fish in the Atlantic Ocean. The question I now have is, are they different? Can I make a conclusion about the fish in the Pacific are laying more fish or less fish or something? If I compare these distributions, I'm going to lay these on top of each other. Right? So now these are like the two distributions plopped on top of each other. Pretty sure that picture's supposed to be opaque, but whatever. Whatever. The distributions, they're there. They are similar-ish, but also a little different-ish. In fact, if you look at the mean value of the blue, we see 17.28, and the mean value of the orange distribution is 17.8. So there's a difference in their means. There's a difference of 0.52, right? So can I just say, well, yeah, there is a difference between the blue fish lay less eggs. Does that seem reasonable to say, especially when you're looking at those distributions? How confident would you be if you're going like, well, maybe, or maybe I didn't have enough data, or maybe this is just like by chance it happened this way. I don't know. Again, this isn't only about fish. This is about any two things. Maybe maybe the gray box is computer science students with blue eyes in a given year. And the light gray box is poli-sci students with blue eyes. Whatever. The question is, like, I want to compare these things. How surprised should I be? So, let's go to an actual example. And the reason I'm using this example is this is the iconic, quintessential example we use when talking about a permutation test. Okay? This is the one, if you go to Google and you type in like permutation test example, 99 of 100 of them are going to be about like, drug trials. So who's here has ever heard of like, drug trials before? Of course you have. And you've heard things like, well, one group gets a placebo and another group doesn't. And the question is, did it have an effect? Is there a difference? We can't just we can't just give one group the new drug and compare it to everybody else because, there might be some other interesting effects. So we'll do like a blind analysis of this where people sign up and we randomly assign them like, okay, here, take this pill. It's a placebo, but they don't know that. And you take this pill. It's a real one. Placebo, real. Like, you don't know what you're getting. So for all you know, you're like, maybe it's a placebo, maybe it's not. So that eliminates any, placebo effect. By the way, when talking about placebos, raise your hand if you've heard the word placebo before. Okay, good. I want you to be very careful. This is an aside from this. Be very careful. Placebo effects are real. If someone takes a placebo and they feel better, they actually feel better. It doesn't matter if it's nonsense. Because at the end of the day, it worked. There's an amazing, anyone ever watched like the Minefield, the guy from, whatchamacallit, on YouTube?
Oh,
Vsauce, yes. He's got one about this, and there are a bunch of kids. This was like in Quebec. There are a bunch of kids that had some like severe problems. One girl had like severe psoriasis or something. Another kid, he got a concussion playing hockey, and then he's had like severe debilitating migraines for every day for years. And they took these kids it was at McGill. They took these kids and put them into an old broken MRI machine. And they're like, oh no, this is brand new technology, it's gonna help you. And the kids are like, oh great. And they go in, and they're all doing fantastic now. The one kid doesn't have migraines anymore. The girl doesn't have issues with like her skin anymore. It's crazy. Yeah?
Yeah, but if they find out it's a placebo, does that ruin the effect?
In this particular example, they told the kids, but it's not clear if the kids understood really what that meant. So I couldn't answer that question. Anyways, be warned, placebo doesn't mean, oh, it's fake. Placebo means it's fake, but it worked. So who cares? Anyways, drug trials. We've got a new drug that apparently is going to help recovery time for some illness, but the question is, does it? Has anyone ever read the description of like, what's the little like thing you put on like canker sores or like cold sores? What's it called? What's that little medication people always put? Whatever. There's something with that, it's got a name that I'm sure if you heard, you'd be like, oh yeah, I've heard of that. If you read the description, it's like, oh, you know, it reduces recovery time by 1 day compared to placebo, right? And then if you read that and you don't really know what that means, you might be like, oh, what's the freaking point? But we'll talk about what this really means. So we've got this new drug that is supposed to help reduce recovery time for some arbitrary illness. So here's what we're going to do. We're going to get a bunch of people. We're going to get a hell of a lot more than just 8 people, but we're going to get a bunch of people. And we're going to randomly assign them to 2 groups. I take the class, I split you down the middle, put half of you over there, half of you over there. You don't know which group you're in. You don't even know who else is in your group. But I just arbitrarily give all the people at that side of the room a placebo, and the other half, the new drug. Right? So we get volunteers, we assign the 2 groups randomly, and the placebo is what we would call like the control group. So here's what happened. After this time, I noticed that the average time it took one person from the drug group was 4.75 days recovery. And the people in the placebo group took 5.75 days. Each individual under there has oh, this person took 5 days, 6 days, 7 days, 5 days, 6, 4, 4, 5, right? And there's the averages. And there's a difference of 1. Wow, the drug appears to certainly help, right? It reduced the recovery time by a day. Which you might think like, well, is it worth it? Well, maybe the drug costs like 2 cents to make and it's a really painful, terrible thing. Yeah, fantastic. Maybe it's not. Maybe we don't care. I don't know. We can start talking about effect size and whatnot, but that doesn't matter right here. It does, but not for what I'm talking about. So clearly the drug works, right? They recovered a day faster. That's fantastic. But the question we have to ask is, with anything, because we've all lived in this world long enough to know that like random funny things pop up all the time. Spurious relationships pop up all the time. Did everyone know that the amount of murders really correlates well with the use of Internet Explorer? Did you know that? Maybe that's a reasonable thing, or maybe not. You want to hear another one that's a relationship? Is ice cream and serial killer sales are related in some way too, I'm pretty sure. Do these seem reasonable? Maybe. Yeah, you say, yeah, maybe if they just had more ice cream, they'd chill out.
That's the exact example I saw for when someone was showing what p-hacking was.
Perfect. And then, like, maybe a relationship is, wow, the relationship between people Googling vampires and Halloween relate a lot. Well, that one seems reasonable, right? you know, we've been around long enough to know that there's a lot of things that are just nonsense, funny things that happen. So the question we have to ask ourselves is, did it matter? Because as we know, any of this stuff could just happen by chance. Maybe we got really lucky in our trial, and it just so happened that our results say it's better. And now I can sell my drugs and make $1 billion. Or maybe it really did just happen by chance, and we're wasting everyone's time and money. So I need to prove to people that this seems to work. And when I say prove, we're going to prove things empirically. We want to demonstrate things with data. If you're coming from a more, you're a computer scientist, and chances are you're familiar with like your math concepts and whatnot. When we're talking about proving things in math, that's a different thing, right? There's like proof, proof, proof. Here we can prove with our empiricism, our observations of data, which is still subject to issues, but we can demonstrate fairly effectively with empirical proof. So, here is where the null hypothesis jumps in. Raise your hand if you've heard the word null hypothesis. Of course you have. Raise your hand if you heard the word null hypothesis and we're like, oh, okay, it means there's no difference. All right, whatever. Put your hand up. Yeah, you did. You didn't really have a sense of where it came from, why it's important, why do we care, whatever. So the null hypothesis is we assume there's no difference, which you all know. But now that we're learning the mechanics of how to compare this stuff, the word null hypothesis starts to actually have some intuitive meaning. So we assume that there is no difference. The null hypothesis, this is where we start. We're going to assume there's no difference. Listen up, this is critically important. The null hypothesis, there's no difference. So if we're assuming the null hypothesis, that would mean, listen carefully. If we assume the null hypothesis, that would mean it didn't matter who went into what group. Right? I could shuffle it. It wouldn't have mattered if the person that recovered in 4 days was in that group or that group, if there is no difference, right? We could just take all of those people, put them into one group, shuffle them up, and separate them again. And we would see that, if we kept doing this, there'd be no difference. It wouldn't matter. If we don't start from the position of the null hypothesis, our assumption is, oh, they are different, meaning that it would matter what group they're in, but that's what we want to show. We need to prove to ourselves that, we need to convince ourselves that there is a difference. So we start from a position of, okay, let's assume there is no difference. And if we go with that assumption, if we have a pile of people over here that recovered, and I know each time how long it took them to recover, if there is no difference, they could have taken the placebo and it wouldn't have mattered. And that person who took the placebo, they could have taken the drug and it wouldn't have mattered. Right? Okay, so if there is no actual difference, then the time of recovery had nothing to do with if they took the drug or the placebo. Therefore, it wouldn't matter which person and recovery time came from which group. That's what I would just say. So here's what we're going to do. We're going to take those people and we're going to shuffle them. There. It's kind of hard to see, but some of them, the ones with the green box were those that were actually in the drug trial group. And the ones without the green box are those that took the placebo. I'm pretty sure. Either way, one way or the other. So I shuffled them. And then I calculate their differences again. So let's start by saying, our first thing we observed was, based on our test, based on our trial, we observed a difference of 1 day. Right? We had those two distributions of recovery times. It's critical that you're paying attention because we're going to start making other distributions that aren't recovery times. They're differences in recovery times. So, we saw 1 day of a difference originally. We shuffle the people and we calculate their average recovery time. Okay? And here, it just so happens that the average recovery time was 0. It just so happened that was the case. But remember, we're coming from the position of the null hypothesis is the case. There is no difference. Which, wow, okay, it's pretty damning. But so far we have 2 observations. We have the original observation, which was -1 day. Then the next observation, which 0 days. Because the -1 day, if it happened by chance, well, that configuration is one of the by chance configurations, right? We're going to shuffle them again. And now I get that. And oh, okay, now there's another difference of -1. A difference of 1.5. And I'm going to keep doing this. I'm going to keep shuffling, compare the differences, and record the difference. I keep getting those differences. Over and over and over and over and over again. I'm going to shuffle this as many times as I can. If I can, I'm going to want to generate every single possible shuffle. If the number of observations we have are too big, that might be impractical. So what we do is we just say, all right, run and do a bajillion of these comparisons. Obviously you can't do them all, but do a lot that we're convinced that we're getting a nice distribution that represents the differences. Did that make sense? Okay, so we have this list of differences. I'm going to plot the distribution of differences. This is the original distributions were distributions that were the recovery times. This is the distribution of the difference in recovery times for the shuffles. This is where I'm going to give you a second to think about what I just said to make sure you've got it, because it's critical. Okay, I'm looking for questions at this stage. Do we have any questions about anything I've said so far? Okay, I'm guessing we're all good, right? So this is the distribution of differences. So the question I'm now asking is, if we're assuming that it didn't matter, and people could have come from any arbitrary group, this is the distribution of what would happen if, they came from any possible arbitrary group. But we did have our original one actual observation. So this distribution is the by chance distribution, right? Distribution of differences if it's just by chance. But the red line is the distribution that we actually observed. So the number of things in total here is the distribution of differences if it's by chance. The number of things to the left, and it's to the left, the direction will depend on what you're doing, which direction matters. We want a lower recovery time, so we're looking that way. The number, let's think about what this means. You can all answer this question yourself. I observed that the recovery time had a difference of 1. -1 day. It was 1 day faster. The whole distribution is the by chance distribution. What would be the total number of the by chance to the left? The number of things that we saw less than 1 day would be the number of things that happened by chance, the number of possible configurations that happened by chance that matched or beat what we observed. This is critical, and this is where you kind of have to make that leap. I'm going to draw it a little bit different. If I've got this nice distribution, can you see that reasonably well? I'm getting no response. Yes? Okay. By chance distribution. Okay? That's my observation. Similar to this, except it's continuous, whatever. That amount right there. All of the things by chance, the number of things that happened by chance that matched or beat what I originally observed. In this case, let's look at what the numbers actually come out to. So, I did 1,000 shuffles. That was overkill because I didn't need 1,000. Yeah.
So is the value that you're looking for effectively like the integral from the absolute minimum to like your observed value?
If it's continuous, absolutely it is.
Okay.
I'm going to say what he just said again. He's like, well, is it like, I'm going to change your words slightly.
Okay.
Is it the area under the curve? Because the distribution is like the volume of things. The area in this area would be the total number of things that matched or beat what I originally observed and what I want to demonstrate is meaningful. So he's like, oh, is it just the integral? Yes. If it's continuous. If it's discrete, we just count. I mean, it's the integral, I guess, too, but it's easy, we just count. So the question is, I did 1,000 shuffles, which was overkill. 152 of those observations, so 1,000 shuffles, 1,000 things that happened by chance, apparently. 152 of those things were -1 or less. Meaning that 152 out of the 1,000 were by chance. So if I ask you, what's the likelihood, what's the probability that if this was happening by chance, if this phenomenon was by chance, based on my observation of -1, what's the probability that this actually did happen by chance? Well, it's the number of things under that curve. Are we okay with this? This is very important. When you're doing your t-tests, when you're doing your man-Whitney, whenever you're doing those things, those are awesome, quick and easy ways to get this comparison. But this is what we're actually caring about. Yeah.
So this is the discrete problem, but like if this was a continuous problem, how would the data observation be framed?
I'm not sure what you mean.
Like how can you recognize that it's discrete versus continuous?
Here, because the way I counted it, I had the values could have been between negative, like, I counted them as like a day and a half, day and a half, right? Maybe it could have been like 0.125. But with the number of things I had, like, okay, realistically, sure, there were floating point numbers, but I couldn't have really gotten 1.010100015921, like, that's not there. So I can be like, well, it's discrete. I could put my finger on each of these things and be happy.
Okay.
Yeah. So, here, like, let's say this again. The whole thing is what happened by chance. The line is what I observed. So I want to say that my drug is better. It beat it by a day. Therefore, what's the likelihood that that actually happened by chance? Well, it's if they meet it or did better. The number of people in the number of times that the random shuffle resulted in a better recovery time would be the how many of the possible configurations, if it really was by chance, how many of those were there where it did happen by chance? Add them up. 152. How many observations did we have? 1,000. Again, I want to be clear, 1,000 was overkill. I had 4 and 4. I didn't need to do 1,000. So I calculated 15.2. There's a 15.2 chance that 15.2% chance that this just happened by chance. Am I happy with that? Maybe. Maybe. It depends what we're trying to achieve. So 15%, is that good? Well, it depends. It means that there's a 15% chance that our drug just appears to improve accuracy. We got really lucky that our random assignment was that. It means that there's a 15% chance that our drug just appears to improve recovery time by 1 day by freak accident. So is that okay? Well, again, it depends. Typically, as per some arbitrary convention, we use 5%. If it's better than a 1 in 20 chance, it's significant. Which then means 1 out of 20 scientific conclusions is entirely bogus, but whatever. But 5% is the arbitrary cutoff that we typically use a lot of times. It's why a lot of people now like to say, they'll report the actual value. In a lot of fields, they'll be like, it beat 0.05, but they don't tell you by how much. They'll be like, it's significant because it was better than 0.05. But yeah, was it like 0.4999999? Because if it was, I'm skeptical. If you ever are writing the p-value was times 10 to the negative 17, okay, yes, it's probably different, yeah.
Something that's just kind of throwing me off, it's a silly question, but the observation line, the red line there, kind of leaves out a little bit past 1. So are there values that are slightly bigger than 1 that are just included in 1?
Really, it's an unfortunate configuration of the bars in the histogram.
Okay.
You'll see that the first bar here had values between negative 1.5 and some value bigger than negative 1, which is really shitty. I should probably regenerate this where I say be between 0, separated by 0.5s. That's why.
So those negative 1 values that are just slightly bigger than negative 1, those are included in the count?
Yes.
As well.
So for all I know, no. It depends. Because if the bucket, this doesn't matter for the permutation test. This matters for how bad this histogram is. I don't actually know, based on this value, I can go look at the actual numbers. But based on that value, all I know is that there's 150 observations somewhere between negative 1.5 and negative 0.8 maybe. Maybe there are none that are less than, in that bar, maybe none of them are actually less than, or more than negative 1. It just so happens that they fell in that block.
Okay.
So it's a shitty histogram. That's the problem. Did we learn something, or are you kind of what? Be honest, because if we're scratching our head, I can try to emphasize a couple of things again, because this is important. Remember, the whole distribution is how many, we're assuming it's happening by chance. So if it's by chance, it doesn't matter which configuration they're in. So shuffle, what's the difference? Shuffle, what's the difference? Those are all, we want to get all or as many of the possible differences where, if it's by chance, it doesn't matter who is in what group. So keep shuffling who's in what group, calculate the difference. Plot that distribution. So that distribution is the volume, the number, the whole thing here. This is the total number of things. These are the total number of observations of some phenomenon, of the difference between phenomenons. That, just by chance. But if we observed a value here, and I want to say that, it makes a difference. If the difference we observed was there, then the by chance of getting a value equal to or better than what I want to show is how many of those possible configurations, this is the total number of configurations, which proportion of them beat, which proportion of those that happen by chance beat what I got. Now, one interesting thing that comes up in this space is, remember how I said we include the negative 1 in one of the observations? Some people won't include the negative 1, some people will. It's just if you don't include the -1, if you don't include the configuration that you observed when assuming the differences, it can have an implication on what the p-value actually comes out to. Because let's say the difference you found is the one possible configuration of the random assignments that actually could get what you observed. Meaning that like you absolutely have something that's meaningful. You've got a difference that absolutely matters, right? So if we have a distribution, let's say it's a discrete one. So it's like, and we've got one little thing here, and there's like 1. That's 1. And we observe this. So the question people ask is like, well, when doing this permutation test, do you consider this configuration? Because that configuration could have happened by chance. So if you do include that configuration, you would say the best p-value you could get is 1 over n, where n is the total number of things in here. If you say, no, we're going to exclude it. We're going to look for things that are exclusively better than. If that happens, we can get a p-value of 0, which some people kind of hate. They're kind of like, well, but you still have that one configuration. Maybe you got so effing lucky that you got that 1 in a million chance to get that one thing that was the best. For me, when in doubt, always make sure you at least include the equal to part. How many of those observations are greater than or equal to? Because then you have no issue of like having a p-value of 0, because some people get really pissy about that. All right, so lose by 1 day. Okay. So we can have a discussion about effect size. If we're happy that our distributions may not be that different, or if we're like, well, our distributions might not be that different, or maybe they are very different, whatever. But 15.2%, I don't know, is that meaningful? But what was the effect? The effect size, like there was a difference of 1, which is kind of a lot if it's a really bad disease or something. Maybe it's like, you know what? There's a 15% chance this happened by chance, but, people suffer a hell of a lot less, so whatever. Or maybe that drug costs $1 billion to make, and it's like, well, that 15.2, I'm not willing to bet on that one. It's kind of expensive, and we're not that convinced that it works. So finding what the p-value is not always the whole story. If you have if you've got n's, if you have like a bajillion observations, so many observations, you can find, like as you increase the number of observations, the more likely you are to find a difference between distributions, because you basically fill in more of those gaps. So you can find a p-value of like times 10 to the -4 or something, and be like, wow, there is a difference. But the actual like difference, here I had a difference of 1 day, but the actual difference that you observe that you're saying is significant is like 20 minutes. It's like, okay, great, there's a difference, but the effect is so stupidly small, no one cares. So it's not only about p-values, there's more to consider. Like if you generate your GA, and you're like, well, I got these results here, but then I turned this knob, I changed something, and my results were here, and it's significantly different. And someone says, how much different? And you say like, by 0.000001. People are going to go, okay, it's different, but who cares? It's 0.000001. All right, so comparing EC runs with different parameter settings. You can do something like this. Compare your machine learning algorithms to another one. You can do something like this. Whatever you want. This is how you compare things. This is what you've been trying to do with your p-values this whole time. The permutation test is probably the most important thing in stats you can learn that no one ever taught you. Which is weird, right? Now, don't get me wrong. That doesn't mean you can't use a Mann-Whitney U test. That doesn't mean you can't use your t-test. That's not what I'm saying. The whole point of this lecture is to tell you what those things are actually, what they mean. Those strategies, your t-test, your Mann-Whitney U's, they're ways to do like the permutation test like easier. It's like a quick and easy way to get a result without having to go through the whole rigmarole of doing all this. It'd be great if you did this, but if you just want like your whatever, do it. The point now though is, now you know what it really is trying to get at. Now you know that the null hypothesis actually has some really goddamn important meaning. If we assume the null hypothesis, then we can assume that it doesn't matter, and that's kind of the whole basis behind this, right? To me, I found this so intuitive. I mean, it took me a while. I didn't get it like that. But once I wrapped my head around it, I was like, that's what we're doing. Where when I saw the formula for a t-test, I was like, okay, here's the magic formula that gives me a magic number that means something, apparently. I wasn't a good stats student. But this is what we're getting at. When you're doing a t-test, you're trying to effectively do this. Oh, if this is the total number of things where it could happen by chance, how many of the ones that could happen by chance matched or beat what I observed and what I'm trying to show you is in fact better? So, if we go back to those original ones, way back here, oh, it's 1205. Well, come on, go to the end. If we go back to the original distributions, the blue and the orange, are they actually different? Well, if you do it, there's an actual difference, is that. Which apparently I don't have the p-value. Oh. Numbers less than 1,000, 17. There is a 1.7 chance that those two things were actually the same. Meaning that the fish in the Pacific Ocean really did lay more eggs, I guess. Anyways, see you later.